Hello, hello. Hopefully everyone can hear me. Let me just get my screen sorted. Hello, hello. Welcome everybody. Let's make sure that goes properly. I'm just going to put my screen over so that I can write properly, but sometimes it turns off, so we'll see what happens. Oh, she's liked me today. That's nice. Hi. Oh, hi, Rob. How are you doing? Lovely to hear from you, even. You finding things? Hello, lovely. Oh, I can't get my pen out for some reason. Good. Lovely to hear from you. How are we all doing? Please, welcome everybody. Welcome back if you are new here. Um, welcome back if you are a returner. Welcome if you are new here. Lovely to have you here. These are our A-level revision sessions that we do most Sundays. And this one is going to be on alkanes. Actually, if you're a GCSE student, there's a lot of content in here that works for GCSE students as well, but obviously it goes into a lot more detail than you need for GCSE. Oh, oh, Rosh, that sounds amazing. Yeah, that sounds fair enough. I mean, university is um, hard work, and especially medicine. There's a lot of interesting people on a medicine course, so I think I can get your vibe there. Um, you're intercalating in maths and computers. Oh, that sounds interesting. I think so. I think I can answer that actually. So you don't know who thought A-level chemistry is relevant to a medicine degree. I think the content, not so much, but the skills it takes to do A-level chemistry is huge for a medicine degree because it's all to do with problem solving, analytics, seeing your way through to a problem, being able to actually understand how bits of the world work and how they work together, the jigsaw puzzle of how everything works. Um, being able to see big picture stuff and small picture stuff. There's some math skills in chemistry or maths in science that is very important. So I do know what you mean, like the content, not so much. There will be some stuff that you will use. A lot of the moles, amounts of substance stuff you'll use, some of the biochem you'll use. But I think it's basically just an understanding of the world and how it all fits together that is really, really important for people if they're doing medicine. If you can't cope with A-level chemistry, you're not going to do brilliantly in degree medicine. Is my thought process anyway. Oh, Lalanza, that doesn't sound like a good idea. Maybe you shouldn't do that. Tiana, hi, lovely to have you here. You don't fancy doing medicine anymore either? You could do biochem. You don't have to do medicine, you could do biochem and still do some really, really awesome, really interesting stuff. You'd say biology, yeah. Well, I think biology is relevant, but I guess you go into a lot more detail in medicine, don't you, than you do at A-level biology. Um, and I think more of A-level biology, from my understanding, more of A-level biology is about memorizing words and phrases, which I guess is important for medicine because you do have to be able to memorize lots of words and phrases and lots of like content stuff for degree level medicine, but there aren't as many skills involved with that, I would say. Trying to get the grades, hopefully reapply for university or something else. Fair enough, Tiana. That sounds like a good idea. You definitely want to go into your degree wanting to do it, whatever it is that you choose to do. So, yeah, if you're getting the vibe now that maybe medicine isn't for you, sounds like a good idea. We'll get started in a second, by the way, guys. Do have pharmacology is quite a substantial part of the course, but they never go into enough detail that you learn from chemistry. Oh, that's a shame. ALD, you hate benzene rings. Love benzene rings. Benzene rings are amazing. Abdullah, do we think that biomedical engineering is a good degree to have? Of course it is. Whatever you want to do is a good degree to have. I think the main thing for me when you go to do a degree is because you're doing at least 3 years of one subject, basically one subject, you have to want to do it. So you either have to have a drive to want to do it to get you somewhere, or you have to have a want to do it because you enjoy it, or both, or an interest in it. One of those three things, or preferably all three things. So either it needs to get you somewhere, so you have a drive to do it because of that, or you're interested in it. so you have a drive to want to do it because of that. Or what was my other one? Interest, or you enjoy it, and so you have a drive to want to do it because of that. I think you need to have a reason to do it, basically, otherwise you're gonna be stuck. Might enter the UK as extra, just taking a gap year. Yeah, that sounds good. Oh, really, Rush? Are they? Oh, that's such a shame. Well, hopefully you can be the grounder, the person that brings everyone back down. Does it have good prospect in the UK? Yeah, definitely. Biomedical engineering does. Yeah, definitely. There's loads and loads of pharma companies in the UK. So yeah. Da, 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 da. Yes, and I mean some degree levels don't, some degrees, sorry, don't necessarily, aren't necessarily going to lead you exactly into that subject, but they may lead you into other related subjects for sure. Right, I am going to get started now because I know that we've got some bits to go through at the end. But obviously feel free to keep having a chat in the chat, and I will dip in and out if we need to. So this is one of our A-level chemistry revision classes. This week we're doing alkanes. If you can, please have a go answering any of the questions that I ask. Pop them in the chat. Feel free to kind of correct each other or what have you if you need, and we will see where we get to. This is just alkanes. We're just looking at alkanes in as much detail and all the different parts of the course as we can around alkanes. But good question, thank you. Okay, right. So a little bit about me. I'm Alyssa. I am the lead chemistry teacher at Snap Revise. I'm the only chemistry teacher at Snap Revise. I've got a PGC in science, specialising in chemistry from Oxford University, and I've been teaching A-level chemistry and GCSE and Key Stage 3 for 9 years now, for 9 years. Just a little bit if you're interested. So Snap Revise run crash courses over the Easter period. I think they're actually a little bit after Easter, aren't they? She says, not 100% sure when Easter is. 29th, isn't it? I think it starts. So yeah, so if you're interested, we run sessions in biology, chemistry, physics, and maths. These are going to be based at the WAL or BAL, I don't know how they pronounce it, Enterprise Hub in London. Or if you don't want to travel into London or don't want to do it in person, or you're not based in London already, then there is a live stream option as well. These are over the Easter holidays after Easter, as it were. We look at exam technique, we cover the trickier topics in the A-level syllabuses, and we provide a seminar booklet that you can take home with you, that you can fill in and take away. And there's also a tutor messenger available throughout the course as well. So if that's something you're interested in, please feel free to head over onto the website to look at, find out more information, or we'll have more info on it at the end of this YouTube session. So feel free to hang around to ask questions about it then as well. Okay, so for this session, we are going to have a look at the trends in boiling points of alkanes and looking at understanding why they are as they are. We're going to look at recalling processes of fractional distillation and cracking. And we're going to look at recalling the equations for the combustion of hydrocarbons and other pollutants. We're not going to look at branched alkanes, which is in OCR. We're not going to look at thermal cracking, because that's only in AQA. And we're not going to look at reforming either, which is only in Edexcel. So if you're in whichever exam board you're in, that's a little section that we don't cover, so you are going to need to look at that yourself. Okay, so if you're AQA, it's this section, these stuff that we're going to be covering from your specification. If it's OCR, then these, and Edexcel, if you're Edexcel, then these. If you haven't already, please feel free to download today's slides from the link below, and then you can use them again, or you can use them to refer back to, whatever, however they, whoopsies, press the wrong button. However they would be useful to you. Right. So let's do a little bit of what do we already know. Everyone should know from GCSE, what's the definition of a hydrocarbon? What is the definition of a hydrocarbon? Go on, don't be shy. Hydrocarbon. What is the definition? Anyone know? So we need to know a word perfectly because it is, yeah, lovely. Well done. So Zauda, sorry if I pronounced your name wrong, Zauda, and Tiana as well, very nice. It is a compound or something that contains only hydrogen and carbon atoms, or contains only hydrogen and carbon. Very nice. And you need to have the word only in there. What is the alkane general formula? Well done, BK. You've already given it to us. That's fab. Feel free, if anybody wants to correct any errors they see, or say that you agree with somebody if you want to. So just double check yours, BK, because I think it's just a typo because you think you know what you're talking about, but you have mistyped something. So just double check. What is the alkane general formula? So for the general formula, nice one, Zachary. For the general formula, we need to have it's not for a specific molecule, so it should cover every alkane as long as it's one of our basic alkanes. By basic, I mean simple. So CN, that's it, well done, BK. H2N plus 2. So you've got twice as many hydrogens as you do carbons plus 2. And that's because of the 2 on the ends of the chain, is how I think of it anyway. So, for example, C4H10. For example, actually 16, I should make that a 10. C4H10. Okay, let's look a little bit at naming then. See if you can do all 6 of these. So if an alkane has 1 carbon, what's the little prefix or the little nomenclature that we use to name it? And actually, you could give me the whole name if you wanted, the whole of the first alkane, the second, the third, the fourth, the fifth, and the sixth. Go for it. See how many you can do. ALD, that sounds great. Let's get us started with methane. Fabulous. What about 2, 3, 4, 5, and 6? Anybody feeling? Oh, yeah. Oh, wow. That looks great. Also, that also looks good. So BK, very nice. Tiana, very good. Samara, fabulous. Oh, hold on. There has been. Oh, Samara, sorry. I think it's again probably just a typo because you probably do know it, but you've repeated propane, so just double check that one. But otherwise, looking good. So methane, ethane, propane. Thank you, Tiana. You're very welcome. Yeah, lovely. Well done, Samara. The butane. Then we go into thinking about shapes, is how I remember it. We're thinking about the numbers that we use to describe shapes. So a pentagon, 5-sided shape, or a 5-carboned thing is pentane, and hexagon, or hexane. Lovely. Very good. Well done. Okay, so let's have a think about these properties then, these sneaky properties. If we were to plot all of the boiling points of our alkanes, and alkanes, straight chain alkanes this is, so unbranched alkanes, so just where you're adding on CH2 again to each molecule to make it a little bit longer each time. This is our trend in boiling point. So general increase. It does taper off a little bit, does get slightly less. The boiling point, sorry, does increase ever so slightly less the higher the number of carbons you get, but it is still a general increase. So why is that? What is happening to the intermolecular forces? What intermolecular forces are possible? And therefore, why is this trend like this? What do we think? So what intermolecular forces occur between unbranched alkane chains? Can we name them? And why is this trend like this then? Very nice. Well done, Sylvester. Well done, BK as well. Good. Fabulous. So the only intermolecular force that's present between alkanes, in particular unbranched alkanes here, but between alkanes in general, are London forces. There's no dipoles, no permanent dipoles, sorry, I should specify, and therefore also no hydrogen bonding. So the only thing that can happen is these London forces, these instantaneous to induced dipole-dipole forces. You might see them written down as van der Waals. So Karim, you could absolutely say van der Waals, but that was actually removed from the specification a few years ago. So they prefer us to say London forces because van der Waals is a little bit too specific. No, wait, which way around is it? Van der Waals is too broad, sorry. London forces are the specific type of intermolecular force. So they prefer us to say London force. Yes, London force is the term for instantaneous dipole to induced dipole forces. That's specifically a London force. Van der Waals is the umbrella, whatever it's called, the umbrella term for instantaneous to induced, induced to induced, and whatever the other one is, I can't remember immediately. So it's a little bit more of an umbrella term. So good. London forces are present and they are weak. We call them weak. So only a little, oopsies, didn't mean to do that. So only a small amount of energy is required to overcome. Small amount of energy is required to overcome them. Hence, we start off with our low boiling points, but the longer the chain, the more London forces we get, so more energy. Very good. The longer, oops. If at any point you can't read my handwriting, by the way, just shout and I will tell you what it's supposed to say. The longer the chain, I should say carbon chain, I'm going to specify, sorry, the longer the carbon chain, the more London forces. You can say greater the London forces. It depends on which scientist you talk to as which they prefer. Personally, I prefer to say there's more of them because you get more places for interactions. But when we're talking about chain length, but if we were talking about, for example, a chlorine molecule versus a bromine molecule, personally, I would say the London force is bigger because you can have a greater difference, greater dipole within the molecule when you've got more electrons. So personally, I would say that a London force is bigger when you're talking about molecule size in terms of number of electrons. If you're talking about chain length, I would say more London forces, but it is a personal thing. The longer the carbon chain, the more London forces. So the greater the energy needed to overcome them. Needed to overcome them. Awesome. Branch chains have fewer London forces due to a lower surface area. Yeah, exactly. Yeah, they do. Congratulations. Well done, they do. Yeah, and ALD is also added in. You can talk about the fact that unbranched alkanes have a larger point of contact or larger surface area through contact, available for contact. Yeah, very nice. Good link. Cool. Let's keep going. So one thing again that we learn at GCSE that we need to know still for A level, it's just the expectation. It's about the same actually, the content. It's just the expectation is that we know it a little bit better. So we can describe it a little bit clearer. We can explain it a lot better as well at A level. So talk me through, give me anything that you remember about fractional distillation. So I'm talking, what's the temperature gradient like? What goes in versus what comes out? What are the trends in the like chain length? What else do we need to know? Viscosity, flammability, all that sort of thing. What do we remember? Is this in the OCR specification? I'll see if I can double check. I mean, fractional distillation is it'll be in all the specs. Okay, it's not in the bit of specification that we've copied into our document, but fractional distillation is one of the separating, what they're called, methods of separation. So you should be able to explain it Whether or not it's a recall bit of the spec, I don't know. So you may not be expected, for example, to recall the names of the fractions, but you should still be able to explain it because it's all encompassed in the bonding and structure module, unfortunately. So yeah, so if that hopefully that answers your question. So you might not have to memorize anything like the names of fractions, but you should still be able to explain it because this is all bonding and structure, unfortunately. Nice, well done, Tiana. Good. Towards the bottom, the boiling point of the species, the fractions is higher. Very good. You don't have to remember the boiling points of the fractions. Absolutely not. No. You do have to remember the trend, but not the boiling points of the fractions. No. So well done. Yeah, good. So these guys have a higher boiling point. Higher boiling point. I'm going to say BP for boiling point because I'm being lazy. Crude oil is what goes in. Very nice. Well done. That's useful. What's the temperature gradient? Does anybody know? Yes, well done, Tiana. Good. So these have longer chains, hence the higher boiling point. I mean, we saw that on the previous slide as well. So again, this is all linking together with that previous content, which we all need to know. So longer chains have a higher boiling point, so that's down the bottom. For example, bitumen, and I can never spell bitumen. Have you spelled it right? I think you probably have. Bitumen. Cool. So shorter chains, lower boiling points at the top. So that's our trend. For example, methane, ethane, propane, etc. are gases. Oh, so Tafara, if you were expected to talk about the trend with branched alkanes, it would be similar. It's just that they would start off with lower boiling points because you can't get as many London forces. So branched chain alkanes, you can expect that even though they are branched, the longer the chain, the higher the boiling point. Same. The trouble is that the amount of branching or how it's branched also has an effect. So if they were going to ask you something like this in an A-level specification, they would have to be so clear to be able to compare something that is very like where only one thing is changing. So, you know, maybe it's a butane chain with a methane off it versus a pentane chain with a methane off it. So you'd only be able to compare those. And the only difference is that you've made the chain longer. So then you could compare it and it would have exactly the same theory. The longer the chain, the more London forces, so the higher the boiling point. But they wouldn't be able to, they wouldn't expect you to compare difference in branching and stuff because there's too many factors at play. You wouldn't be able to explain it. Yes, good, Sylvester. So it's hotter at the bottom, colder at the top. Yeah, lovely. Well done, ALD as well. Hot at the bottom, cool at the top. I wouldn't say cold, I guess. I think I did just then, but cooler at the top. So the gradient is opposite to what we often think about when we think about hot and cold. We usually think hot things are less dense and so tend to float. That is true, but here the temperature gradient is forced to be hot at the bottom, cool at the top. That means as hydrocarbons rise up through the column, they condense at the temperature below their boiling point. So hydrocarbons are separated by rising through the column and and condensing as they reach their boiling point. So even though they're condensing, we still use the term boiling point because that's the label for them for the point at which they boil. So even though actually they're going the other way, they're not boiling, they're condensing. Sorry, didn't mean to do that. They're boiling, not condensing. We still call it a boiling point, just in case anyone's confused about that. So rising through the column and, cooling, I meant to say cooling and condensing. Cooling and condensing as they reach their boiling point. That's how we separate them. Shorter chains have a lower boiling point. Longer chains have a higher boiling point. and the ones in the middle tend to be our liquids. Okay. Awesome. Good. Don't forget, I won't go over it now, but don't forget you also could potentially be asked to talk about viscosity. So longer chains are going to have a higher viscosity because they're going to have greater interactions between chains, so they're not going to flow as easily. Think about, golden syrup versus water. Golden syrup is very viscous, it doesn't flow very well. Or you can also think about rice, short chains of rice versus long pieces of spaghetti. Rice pours really easily. Spaghetti doesn't pour, it bloop, in a lump. So another way to think about it. And also, hopefully, we should be able to explain that these smaller chains are going to be more flammable because will have a higher what's the volatility? They're more volatile, so they turn to a gas easier, evidently, because they've got lower boiling points. So if they turn to a gas easier, they're going to be more flammable. So shorter chains are going to be more flammable as well and less viscous. Okay, let's keep going. So cracking, this is something which we apparently haven't found in the specification for OCR, but it has been in past papers. So if you're an OCR student, you have a think about it, but you probably won't be expected to recall. You'll probably just be expected to apply other knowledge about this. But catalytic cracking is when we have longer chained hydrocarbons that we then break down into more useful compounds using cracking. That's the point of cracking. And if you remember anything from this slide, it's that the reason we do this is because shorter chains are more useful. They're more flammable, they're less viscous, and we have more uses for them. So they're more useful. So it was better if we have shorter chains. So let's say we crack our molecule there. When you do cracking, one of the common errors, usually only at GCSE, so hopefully we find it out by the time we get to A level, but one of the common errors is that we forget that when we crack, there aren't enough hydrogens. Now, the way we crack it as well is that there's a little bit of a shift in atoms so that we end up with one alkene and an alkane, whatever's left over. 1, 2, 3, 5. 1, 2, 3, 4, 5. So we end up with an alkane and an alkene. So even though we have broken our longer chain there, and at the moment there are 5 hydrogens on the left and then the rest on the right, the way that cracking works, especially catalytic cracking, is that one of those hydrogens actually jumps ship over to the right-hand part of the chain. So we end up with one alkane and one alkene. Anybody know a good description for the catalyst that we use? What is the name of the catalyst? Or does anybody know the chemicals that you can use in the catalyst? Or, no, let me rephrase that. Does anyone know what elements the catalyst is made out of? Yes, zeolite, good, is the structure, fabulous. So, a catalyst, so zeolite catalyst, which has a honeycomb structure. Why do we have a honeycomb structure? Honeycomb. Oh dear, sorry. Structure. And good, it is aluminium oxide. So we can have silicon dioxide, aluminium oxide. Is one, or you can just have aluminium oxide. Lovely. Good. And honeycomb structure because we have a larger surface area while still giving it structural integrity. But the thing they're looking for in the exam is a larger surface area. Very nice. Well done together. Brilliant. Okay. So one of the things that I would recommend everybody do, even if you're not in the middle of a session with us, is to, as you're doing your revision, either after you've finished your revision or when you're partway through, is just to take a second to evaluate how you're thinking. Evaluate your revision, evaluate whether or not you think your plan is working, and how confident you're feeling about your learning. So we pop these into our sessions as well, just as a reminder, because also it's useful for you guys, but also it's useful for us. So how confident are you feeling about your learning? So you can give me a 1 or a smiley face if, yeah, you're quite happy with what we're doing. This is great. It's all going well. Give me a 2 or a face if, yeah, it's okay. I mean, some of it isn't making sense. Maybe I'm going to need to go back over some of it, but yeah, it's all right. Or you can give me a 3 and a if actually might be the first time you're learning about it and actually you've got no idea, you're not keeping up. Or this is something that you definitely have got some missed connections on and you're going to need to spend some time to practice it. Awesome, we've got a couple of 1s. Lovely. If you don't want to give me a number, that's absolutely fine. But it's always good, at least if you do, just evaluate yourself. Just have a think. How are you finding it? Is it okay? Lovely. Okay, how are we doing for time? I might do this question, but maybe not the next question, exam question, because I don't want to run out of time and I've got a bit of stuff to say at the end. So we'll have a go at this question, this exam question, and then if we have time, we can come back to the second one in a minute. So 4 marks. Outline the essential features of the fractional distillation of crude oil that enable the crude oil to be separated into fractions. So, thinking about your GCSE level knowledge and your A level knowledge, what is necessary, so essential features of the fractional distillation of crude oil that enable it to be separated? How do you know that it can be separated into fractions? What must be happening in fractional distillation for it to be separated into fractions? 4 marks, so we need to say 4 things. What do we think those 4 things are? Anybody want to suggest one of the points that we could say? Yes, we need to talk about different temperatures. Specifically, though, I want you to be specific if you can. High temp, again, I'm going to need specifics. What do we mean by high temperature? Are you talking about a high temperature within the column, or are you talking about a high temperature of stuff going in? We need specifics. One of the things that you've probably heard from your teachers, I'm sure, is that you have to pretend that examiners are not very clever. You have to make sure that you tell them everything that's in your head so that they know you know the answer and that they know you know what you're talking about. Yes, good. Okay, lovely. So different boiling points due to different carbon chain lengths. So I'm going to put it round the other way actually and just say different carbon chain lengths cause different boiling points. Can we be more specific? Technically, that is worth a mark. Can we be more specific for another mark? So which is going to be which? Small molecules condense at the top. Lovely. Let's say that. So smaller or shorter, you could say, if you want to talk about chain length. Molecules. Oh, my rubber is not working. That's good. Condense at the top. Oh, has everything just disappeared for you guys? Has all my writing gone? Because it's just disappeared for me now, for some reason. I'll write it again. I think it has gone. Apologies if you're now going to see it written twice. What did I say? How do we say it? You said different carbon chain lengths. Cause different boiling points. We've said, thanks, Tiana. Sorry, I don't know why that's done it, but never mind. smaller or shorter. No, the rubber's still not working, that's annoying. Shorter chains have, come on, brain. No, you said condense at the top of the column, you could say. Longer chains condense bottom, evidently, but we need to still say it. And one of the things which Destiny, you've kind of included in your point, which is very good, but I'm going to say a little bit more explicitly, is that there is a temperature gradient. Can't spell temperature. Temperature gradient, which is cool at the top, hot at the bottom. Why has it just deleted everything again? I don't know why it's done that. I'm not going to write it a third time. Goodness, silly thing. Sorry, guys. Hopefully you've got that down. I've said it all anyway. So those are the 4 points that you need to say. There's a temperature gradient, and you need to explain what the temperature gradient is. Or you don't have to have said that, but you need to have included in your points about the longer chain, higher boiling point. You can say that longer chains have a higher boiling point and condense at the hot bottom. So as long as you include stuff, thank you, Tiana. As long as you include stuff about the temperature gradient, the size of the chain, and where it condenses, then you'll get all 4 marks. And the fact that different chain lengths have different boiling points. So long as somewhere in your answer you've said those 4 things, you will get your 4 marks. Technology, eh? Right, I'm going to skip that question for now, just so that we don't run out of time, and have a think about combustion. Yes, higher volatile ones are collected at the top. That's also a very good point as well, Tafara. I would just talk about the chain length that makes it more volatile. So shorter chain length makes it more volatile, just to make sure you get all the marks. And you could also have talked about crude oil being in mixture. That would also be, yeah, lovely. Unknown girl, that's good as well. So similar boiling points, condensers in the same fraction. Yeah, the fractionating column is the whole thing, so the same fraction. Yeah, lovely. Okay, so combustion of alkanes. Let's do a little bit of combustion. So let's assume that these are all complete combustion. Can you write, and obviously you guys can't really do your subscript, but we're going to assume you know how to write subscript. Can you write me an equation for combustion of methane, complete combustion of methane? So at GCSE, you might have to balance this, or you might have to give the products. At A level, we have to be able to write it from scratch. So what is the equation for combustion, complete combustion of methane? Balanced as well, please. Have a go at that. If you're not sure, I'm going to get started slowly. So first things first, but please feel free to have a go and pop it in the chat when you're done. First things first, methane. We need to know the equation for methane. Oh, now I've got a random couple of words at the bottom written on my screen. Oh, I don't. Okay. What's the formula of methane? Methane's our first alkane. We need to know the formula of an alkane. It's CnH2n plus 2. So if we've got 1 carbon for meth for 1 carbon, it must be CH4. So 2 times 1 is 2, plus 2 is 4. If it's complete combustion, well, if it's combustion at all, we know there's got to be some oxygen involved. And we produce complete combustion, always produces carbon dioxide and water. Very nice, well done. Got that as well. Looking pretty good. Let's just double check our numbers for some of us. But actually, I think you might have got them right, but I haven't double checked. So carbon dioxide and water. We don't need state symbols here because the question hasn't specifically asked for it, but also the process does not require state symbols. So we don't need it. Right, 1 carbon on the left, 1 carbon on the right. Carbon's done. 4 hydrogens on the left, 2 on the right. So I'm going to need to add in a 2 waters to get to there. Lovely. Then I've got 2 oxygens on the left and 1, 2, 3, 4 on the right. So I'm going to need 2 O2. So very well done if you said that. I'm just going to see if that gets rid of everything. CH4 plus 2O2. Oh, it's gone really weird now. Not sure why it's doing this. I'm going to write in a different colour so that it doesn't write over the top. Now it's just put it everywhere. I can't rub it out. What is this technology doing? Oh my gosh, I don't know what's happening. Okay, I'm going to just have to try my hardest not to make any errors, I think, and hope that it disappears in a second. No, it's going to be on all over my slides. Right, I'll tell you what I'm going to do. I'm just going to close that down and then bring it back up again. See if that works. Right, let's try this. Okay, hopefully it just needed a break. Sorry about that. I don't know what technology was doing there. Okay, what about propane then? Sorry about that. But let's do propane. Well done to those of you that correctly wrote the balanced equation. What about propane? What's the balanced equation for propane? Again, feel free to go ahead and have a look, but I'll do it nice and slowly. So first of all, we need to know what propane is. Meth eth prop, or mice eat peanut butter. Meth eth prop. So P for prop means 3 carbons. So C3, it's an alkane. The general formula is CnH2n plus 2. So that must mean it's C3H8. It's also combustion, so it has to be with oxygen. It's also complete combustion, so it must produce carbon dioxide and water. And now we've just got to balance it. Right, nice one, Tiana. That looks good. Let's just double check. So 3 carbons on the left, so I need 3 CO2s on the right. 8 hydrogens on the left, so I need 4 waters on the right. And then I've got 3 times 2 is 6, plus another 4, 10 oxygens on the right. So I'm going to need 5 O2s to get 10 oxygens on the left. Always, whenever you're balancing equations, start with the most complicated looking molecules and end with the ones that have got a single element in them. So O2 has only got oxygen in it, so you're going to need to you can balance that last, balance oxygen last, because that O2 is going to make it much easier to balance. Whereas the other molecules all have more than one element in them, so you need to try and sort those out first so that they don't mess everything else up. Lovely. Okay, so the general combustion equation, sometimes we have seen in past papers, they ask you to deduce this or to use it, which is a bit mean. So you can memorize this if you want to, or just write yourself an equation for a basic combustion and then work it out. But if I just give you the formula now, you can memorize it if you want or use it if you want. So if it's CXHY, so you've got X numbers of C and Y numbers of H, then your oxygen, actually we'll come back to oxygen in a second, because we know you've got to have X numbers of CO2, because you've got to have the same number of carbons in both. And you know you've got to have Y/2 numbers of water, because you've got 2 hydrogens in water. So you've got to have the number of hydrogens in our hydrocarbon divided by 2 numbers of waters to make sure you've got the same number of hydrogens. And that therefore means you must have X plus Y over 2, all divided by 2. So to make it easier, we'll just do X plus Y over 4 numbers of O2. And then it balances. So feel free to memorize that, or you can just work it out if you know how to balance an equation. How are we doing for time? I might speed up a little bit because we are a little bit behind. Okay, what about incomplete combustion then? So this is something that you will need to talk about either written, so describe incomplete combustion, or you may be asked to write a balanced equation. But if they do, they need to give you some more information to do with the ratios of products. So, for example, let's say that we know we're going to be producing some carbon monoxide and some carbon dioxide, and obviously water, because we have to produce the water. We've got, we know we're going to need to have 4 lots of water to balance the 3 hydrogens. If you think about it ratio-wise, if you add any more carbon dioxides, you're going to make the oxygen number go out. So it's the easiest way to balance this, just to stick a 2 in front of the carbon monoxide. If you get to a question like this where actually the ratios could be different, good question, Tiana, we'll come to that in a sec. If you get to a question like this where the ratios could be different, then there should be more than one answer in the mark scheme. So don't have a minor panic if you think, oh my God, but actually it could be one or the other and they haven't given me any idea as to which it is, then there will be 2 answers in the mark scheme. But as you have just specified, Tiana, they should give you more information. So they should say that soot is produced if they want you to include carbon, or they should say that soot isn't produced if they don't want to, or they should say only carbon monoxide is produced as an incomplete combustion product, or something like that, so that you know what is expected of you. So yes, if it's not specified, you should be given all the information you need in the question. So if something isn't specified, assume it's not there. Yeah, good question though. So soot, or sometimes they call it smoke, or sometimes they call it particulates, or sometimes they just call it carbon, particulates, etc. Could also be produced, in which case it's just carbon. And let's say they also say carbon dioxide and water are also produced, have a look at balancing it. Again, we'd do a similar thing. We'd have a look. We've got 8 hydrogens, so I'm going to need 4 waters. With the carbons, I'm going to need to include at least 1 carbon, but as soon as I start introducing more carbon dioxides, I'm going to unbalance the oxygens. But actually, 1, 4, 5, 6. Well, actually, so again, this is one where there's actually a couple of different ratios. Personally, I'm going to, because I haven't specified, I'm going to say 4, 5, 6. Yeah, okay, so I'm going to put 2 carbons. So I've got my balance my carbons, and then I've got 3 O2s to balance the oxygens. 4, 5, 6, yes. If they don't specify, then they don't care. So do your best. Okay, we also need to talk about a little bit about pollution. So nitrogen oxide, where does the nitrogen come from? Why do you get nitrogen oxides produced as pollutants specifically in car engines? Where does the nitrogen come from? Again, this is GCSE stuff, but we also need to know it for A level. From the air, very good. The air, lovely. Also, that's a question. Carbon is the black thing at the bottom of a calorimeter when it's under a Bunsen burner, right? Yes, it is, absolutely. That's the soot. Yeah, that's the carbon that's produced. Yeah, correct. Very good. Well done, unknown girls. Well, it's from the air. Where does sulfur come from? Why do we get sulfur oxides produced again in combustion in cars? Where does the sulfur come from? We've just looked at combustion. There was no sulfur, there was no nitrogen. We know nitrogen comes from the air. That's why we get nitrogen oxides produced in combustion in cars. Where does the sulfur come from? Yes, it does. Well done, Tiana. Congratulations. Really nice. Impurities in the fuel. They should, technically, fuels should have the sulfur removed. Supposedly, most of it is removed, but there are still some impurities. But it is important to recognize that there's a difference. Sulfur comes from impurities in the fuel, nitrogen comes from the air, and that's why we get these 2 pollutants, nitrogen oxides and sulfur oxides. Because we're a little bit low on time, I'm just going to write out some equations. They might present this to you in different ways. So we just, as chemists, need to be able to interpret the question they're giving us and come up with a reasonable answer. So let's say they ask us to explain where nitrogen oxide and nitrogen dioxide. So let's say nitrogen monoxide is going to be produced when N2 and O2 combine to make two NOs. But we could also get nitrogen dioxide produced if we react with another molecule to produce a molecule of oxygen, to produce NO2. Why is that important? So this is all at high temperature, sorry, I forgot to say. At the high temp in a car engine. Why is that important? It's important because NO2 is acidic in solution, therefore produces acid rain, or is one of the causes of acid rain. Not so good. What about sulfur? How does sulfur interact with oxygen? Well, again, we can produce sulfur dioxide really easily. As a chemist, hopefully you can work out that equation nice and easily. But you also just might want to have a look at how we then produce sulfuric acid. So sulfuric acid, you're going to need a little bit of a further reaction with oxygen and water in the air to get sulfuric acid, sorry. Is that right? 1, 2, 3, 1, 2, 3, 4, yes. So that is, again, obviously, then falls as acid rain. So both of these, not good. When will we do Unit 5 chemistry? You're going to need to specify, I'm afraid. I don't know which Unit 5 is. If you have a look back through the YouTube, there's loads of stuff back in our YouTube. So feel free to have a flick back and look back through previous web classes and YouTube classes, lives and all that sort of thing. Because we might have done the one that you're thinking about already. Right, have a think about how confident you're feeling about that. It's a lot of equations, and as an A-level student, I particularly remember thinking, oh my gosh, I have to remember everything. It's horrible, so much to remember. And it is a lot to remember. But if you can understand how things interact, or if you have a good understanding of ratios and how many bonds different elements want to make, you don't have to memorize it then, because you can work it out. Okay, so it does feel like a lot, but even if especially if you have an idea of where you're heading for, you can work it out in an exam, so you don't have to memorize it all. If you want to memorize it all, please feel free to. That's, it's totally up to you. Okay, lovely. So just have a think how you're feeling. Unfortunately, we are a little bit low on time, so I'm gonna not be able to go through these exam questions. So I just want to see if anybody has any questions, and then I'm going to go through briefly a little bit about the what they call revision crash courses. Is there lives for the rest of organic? There's definitely lives for some of them. If you go back, there's definitely lives for some of them. I don't know how much of the course we cover in our lives though. So you'd have to do a bit of searching, unfortunately. But thank you for asking the question. But yes, I'm not sure, I'm afraid. So hopefully we know trends in boiling points for alkanes. We have an understanding of the process of fractional distillation and cracking, both associated with alkanes, and equations for combustion of hydrocarbons and other pollutants. Does anybody have any questions for me about that content before we disappear from it? I'll just give you a second in case you do. Don't worry if you don't, that's absolutely fine. Cool. Okay. Well, I'll just spend a couple of minutes talking about our crash courses. So I mentioned that, oh gosh, try and talk. I mentioned them at the beginning of this session. So Snap Provides run crash courses. They have done them at Easter for the last couple of years, for a few years. And they run them in biology, chemistry, physics, and maths. So just to give you an overview of what the crash course is, feel free to head onto the website and read about them if you would like. But what we look at is exam techniques. So we look at how to break down questions and interpret command words, something that lots of students find very difficult. We look at a range of question types that will come up in your exam, and we look at a step-by-step approach to writing full mark answers. It feels a little in depth when we do this in the crash course, but it is so useful, I think, for helping students to do this quickly, mentally, in their head, when they approach an exam question in an exam or when they're doing practice. So it's really important to get a little bit of exam technique done. We then spend the rest of the day, either in the year 12 day or the year 13, so AS or A2 days, looking at trickier topics. So we pick some of the trickier topics from AS for the first day and A2 for the second day and revise them. We give opportunities for people to ask questions, and we look at using the exam technique skills from the morning to answer some difficult questions from those harder topics. If you come along to the course, or if you go choose the live stream option, then you will be provided with a seminar booklet. So you can complete it throughout the day. You can add in your own notes. So either the notes that the tutor on stage gives or your own notes if you want. It's an incredible take-home resource because it has loads of questions in it. And it's jam-packed with extras like mock exams and topic tests and stuff, as well as answers. So you do get provided with answers as well to check your work afterwards. And then we also have this thing called a tutor messenger. So throughout the days, there are additional support tutors on the end of a phone or tablet, web page, web, however you want to use it, to answer any questions you have. So say somebody uses a word you're not quite confident with using, or maybe an explanation has been given that you haven't quite followed and you want a little bit more in depth, you can message the tutor throughout the day to get more in depth knowledge, or maybe you just want to stretch your knowledge a little bit outside of the syllabus. You can use the tutor messenger for that, and you can ask as many questions as you like. So where are they? So if you want to be in person, they're at this Vol Enterprise Hub in London. Or if you want to do it from the comfort of your own home, you can live stream it via Zoom. So there's physics, Tuesday and Wednesday, the 2nd and 3rd of April. Maths, Thursday, the 4th of April, Friday, the 5th of April. Then chemistry with me on Monday and Tuesday, the 8th and 9th, year 12, then year 13. And biology on Wednesday and Thursday, the 10th and 11th. If you're interested, please feel free to head over onto the website to get more information. So snapprovise.co.uk/seminars for more information to find out about costs and how to book and all that sort of thing. But otherwise, does anybody have any questions, queries, issues? Please feel free to pop them in the chat. Otherwise, we can head off. Best of luck with all of your revision at the moment. Hopefully see you at a future web class or a future live. And like I've said a couple of times, please feel free to look back through the back catalogue if you want to. Hopefully all of the slides will still be there in the link below, so you can download the slides to use for your own revision and to go through the class live, as it were, rewatching it. You can always rewatch it at 1.5 speed if you fancy, just to speed it up. But yes, please feel free to do that. And I will hopefully see you next time. Thank you, Tiana. See you next time. That's lovely. So BK, let's say you've been getting consistent A's in exams for chemistry, and the end of years you got B. Can they bring it up by 1 for predicted grades? I would say talk to your teacher. So I had this with my A level, almost exactly what you've just said, where I consistently did really well, and then my predicted grade was a B, and I said, how can I have been getting A's in my end of topic tests and you predicted me a B? And my teacher decided to tell me that he believed that I wasn't putting in the work outside of school, but it was only because I hadn't been showing him. So I then presented to him with all the work I'm doing outside of school, and he said, okay, apologies, I wasn't aware of this. And so we had a conversation, and he did change my predicted grade. So I would suggest you go and talk to your teacher or tutor. If you want to talk to your tutor first and then get them to talk to your teacher, you could do that if you wanted. But I would say, yeah, have a conversation with somebody about it, because it might be that actually they they just need to see evidence from you that you've been working harder than they've seen. Perhaps maybe you've forgotten a couple of homeworks, and so they're thinking you're not doing the homeworks or whatever it is. So yeah, I'd go and have a word with them about predicted grades. How much of the crash course? Okay, so I can't answer any of those questions actually, I'm afraid, because I don't know the answer. But all the information should be on the website. So if you wanted to head over to the seminars, I will say in previous years they have done discounts. So I presume that they will do. but I can't say for certain because I haven't been given that info. Um, the crash courses are 1 day long per year. So AS chemistry, for example, is on 1 day. A2 chemistry is on a second day. So if you were going to do both the whole, it's not the whole of the course, of course, you can't do the whole of an A-level course in 2 days. But if you're going to do the whole year 12 and year 13, it's 2 days long. If you're in year 12 and you just want to do 1 day, then obviously you can just do 1 day. That's absolutely fine because year 13 wouldn't be useful to you. So that's absolutely fine. But if you're in year 13 and you want to do both, absolutely you can do both. Da, 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 da. So again, I believe they do offer discounts, but I can't tell you how much that is because I don't know for certain. Is it for the full 2 years, AQA specific? It's general. So it covers AQA, EdXL, and OCR. If there are major discrepancies between the exam boards, then we point them out, like we do in our web classes here and lives. So if there's major discrepancies, like different reagents or something isn't included, then we do mention it. And so yes, general, but we do try and give you hints about the differences between the exam boards where appropriate. A lot of the content is across all three, and it's the same. So there was a huge overlap between the exam boards. Is the AS chemistry included for A2 syllabus as well? I think, if I'm understanding your question right, Abdullah, then no is my answer, because we just look at A2 content on the A2 day. So the stuff, like equilibrium 2 and kinetics 2 or whatever for the A2 day. So we don't recover any AS content on the A2 day. I think that's what you're asking. In exams, then you are expected to know both AS and A2 syllabus for your exams at the end of the 2 years. Yes. So in terms of the seminars, no, we don't recover AS content on the second day. But in terms of exams, of course, you are expected to know all of it. Oh, thank you, BK. That's lovely. That's very useful. Thank you very much. £100 per ticket for in person. So that would be £109, sorry, £109 per day. Okay, fabulous. Right, I have run over, so I'm going to need to go. But thank you so much for being so involved and for being here. Hope to see you at a future web class and or at the crash course. Awesome. Thank you very much, guys. Bye. Thank you very much. Cheers. Bye.